Okay, so we saw how we had to determine rate laws based upon experimental data, but where does that experimental data come from? One of the ways that we can get it is through spectroscopy. We've looked at spectroscopy before. This is Beer's law, where we shine a light through a particular sample. The intensity of the light that makes it through the sample tells us the concentration. Basically, as we shine a light through our sample right here, that sample is going to absorb a certain amount of that light, and then a certain amount is going to make it through. So the more concentrated it is, the darker this is going to be. The darker it is, the less light that makes it through. And so we can use that then to figure out what concentration is. So Beer's law, the one that we looked at before, where A is the amount of light that's absorbed, is equal to lowercase a, which is the molar absorptivity. That's a constant for a particular reaction. And then the path length, which is just be the size of your cuvette, divided or times the concentration, which is in molarity. Okay, so here's an example that we're going to do together. We've got a particular reaction. We're reacting B with C, producing D plus E. And so with this reaction, C is a green color, everything else is colorless. And so we're going to use our cuvette, we're going to use Beer's law to measure the disappearance of C, which is green. And so right here, we would get the absorbance versus time for 3 different reactions. And look at this. For 3 different reactions, we did 3 different combinations of concentrations. So between experiment 1 and experiment 2, we kept B the same but doubled C. That's going to come in handy for figuring out some rate law. And then for 2 to 3, let's see, we changed both of them. But if we go from experiment 1 to 3, we can see that we kept C the same but doubled B. So that means we're going to be able to figure out the order with respect to B and C based upon this data right here. To do this, we're going to need to figure out the change in concentration over the change in time. And so right here, we do have the time on the bottom, but we're not measuring the concentration right there or the rate. We're measuring the molar absorptivity, or the absorbance. So that means what we're going to need to find is the change in concentration. Well, let's remember Beer's law, which is A is equal to A, B, C. C being the concentration. So if we can figure out what the concentration is at each one of these little points right there, we can figure out how the concentration changed over time. So sticking with our equation, A equals ABC, we know what A is for a particular reactant, or we can look on the graph to figure it out. B is the size of the cuvette. We were told in the question it was 1 centimeter. We're trying to figure out C, but first we need to figure out A. So if we figure out what A is, that's a constant, and so it's going to stay the same for all of the experiments, so we'll just be able to use this number over and over and over again. So to figure out A, I'm just going to use the data from experiment number 2. Why experiment number 2? Because the initial concentration is a nice even 1, and I wanted to use 1 on top. You could use any of the 3 experiments, though. You're just looking at the initial concentration of C, and then using the initial absorbance, which we can see on the graph. So at time 0, when the concentration would be what it shows at the top of the question, and then the absorbance is on the y-axis of our graph. And so right here, then plug those numbers in, and A would come out to be 5.0 molar inverse centimeters inverse. And so those would be the units, just canceling out. Nothing cancels out but that right there. And if you use any of those 3 initial experiments, you'd get the exact same number. All right, so now we need to figure out the initial rate for each of those experiments. These will be the rates then that we compare in order to figure out what the rate law is for the overall reaction. And so just remember from the very, very first video what rate is equal to. Rate is equal to the concentration, change in concentration, over the change in time. Yes, rate is also equal to K times the concentrations to their order, but we don't know any of that stuff yet, so we've got to use a different way to calculate rate. We're going to use the basic change in concentration over change in time. In order to figure this out, we need to know what the concentration was at the end of the experiment. For the first experiment, we know what it was at the beginning of the experiment. We just need to figure out what it was at the end, and we'll do that using Beer's law to figure out C. And so C is going to be equal to A divided by AB. Now that we've figured out what A was in the last slide, we can use our other numbers to figure out what the concentration was at the end of the experiment. And so for this first one, the absorbance, if you look on the graph, is 0.375. And it's going to be divided by the molar absorptivity, which we said was 5 centimeters inverse times molarity inverse. And that is multiplied by, it's getting messy, 1 centimeter. And so what's going to happen here is centimeters are going to cancel out centimeters. We're left with molarity. We find out that the final concentration is 0.075 molar. And so then plugging that into our rate, it's going to be a change in concentration, which would be the final concentration minus the initial. And so the final is what we just found at 0.075 molar. Sorry, let's clean that up a bit. Minus the initial concentration, which was 0.01 or 0.10, sorry, molar. And that's divided by time. If we look on the graph, it goes for 60 seconds. So we'll divide it by 60 seconds. And that tells us the initial rate for experiment 1 is 4.2 times 10 to the negative 4th molar per second. 4.2 times 10 to the negative 4th molar per second. All right, and we can do the exact same thing for the other 3 experiments. Looking on the graph, figuring out what the absorptivity was at the end of the reaction, so after 60 seconds, plugging it in to figure out what the final concentration is, plugging that into the rate law, and getting the different rates. I'm not going to go through and do all of them. You can do them if you want. Check your answers with mine. So then the rate of the second reaction winds up being, I get 8.3 times 10 to the negative 4th molar per second. And then the rate for the third reaction I get is 8.3 times 10 to the negative 4th as well. Hopefully you get something similar. So then finally we finish up by making a chart, and this is what we're then going to use to figure out our rate law. What do you know, this chart looks a lot like the experimental data from a different experiment or from the practice problem we did before, and that's just what we're going to use it for. So now we can compare the changes in concentrations to the changes in rates to figure out what the order is with respect to B and C. So for this, I'm going to show you a different way to figure out what the reaction order is. This way, it's a little bit messier. There's a lot more going on, but it works 100% of the time. The method I showed you before in the last video works 98, 99% of the time, but this one is a surefire method. It just takes a little bit longer to do. So in this one, you just use the same rate factor. And so we're going to look at experiment 3 to experiment 1, because from 3 to 1, the concentration of C stayed the same, but the concentration of B doubled. And so you would just compare the rates from 3 to 1, and then you would divide it by, instead of just the concentrations, you would put in the actual rate law in there. And so since C is staying the same in this case, that means that C is the same on top and on bottom, which means it cancels out. Also, K is the same on top and on bottom, and so it cancels out as well. What you wind up with looks a lot like that equation I showed you before, but where this setup comes in handy is where C maybe doesn't stay the same. Okay, every once in a while we'll have ones where B and C both double, and you would have to use this particular setup, but we're fine for this right here. But we can go ahead and plug those numbers in just like old times. And when we do that, we see that the rate essentially doubled, and the concentration also doubled, which means that this is a first order reaction with respect to B. And we can do the same thing to figure out C with reaction 2 and 1. And in this case, since B stays the same, B's cancel out. K's, since they stay the same, they cancel out. We wind up with the setup just like before. And so in this case, we can plug the numbers in from 2 and 1. And when we do that again, we see that the rate once more doubled, and the concentration also doubled. And so that means that M is also going to be equal to 1. So that means for this particular reaction, it's first order with respect to both B and C. So then finding the rate law, that just means that the rate for this particular reaction is going to be equal to K, the constant, times B to the first and C to the first. So rate equals KBC. And what do you know? It wants us to find the rate constant K. So once more, we just take one of the 3 reactions and we plug in the values from that particular reaction in order to solve for K using the rate law. So K is going to be equal to the rate for the particular reaction we chose times the concentration of B to the first times the concentration of C to the first. And so I just picked one of the reactions data from any experiment, and I plugged those numbers in. Connor, did you notice how I put my units on every stinking number out there? Did that for a reason. I did that so that I can cancel things out and figure out what the units on K are. So in this case, we've got molar on top and molar on the bottom. We're left with seconds on the bottom and molar on the bottom. So that means the units for this particular K are going to be molar inverse times seconds inverse. And so we could plug those numbers into the calculator and we would get 0.042. And that's molar inverse, seconds inverse as our units. And so that would be the final and complete and correct answer.